Every day, millions of people type questions into ChatGPT and get answers in seconds. It feels almost magical. You ask a question in English, it understands, it thinks, and then it replies, almost like talking to another human. But here's the surprising part. ChatGPT doesn't actually understand language the way humans do. It doesn't think in words. It doesn't think in sentences. In fact, inside the model, there are no words at all, only numbers. So how does a machine that only works with numbers generate paragraphs of perfectly readable text? That's exactly what we'll uncover in this video. Before we dive into the details, let's take a look at the entire journey a prompt takes inside a LLM. When you type a message into ChatGPT, it might look like the model is reading and understanding words just like we do. But that's not actually what's happening. The very first step is called tokenization. Your text is broken down into smaller pieces called tokens, and each of those tokens is assigned a numerical ID. At that point, the model is no longer working with human-readable text. It's working with numbers. Those token IDs then enter what we'll call the generation loop. First, the token IDs are converted into embeddings, numerical representations that carry meaning. Those embeddings then flow into the transformer, the neural network at the heart of the model. The transformer processes the entire context and calculates scores for every possible next token it could generate. Those scores are then converted into probabilities, and from those probabilities, a selection process called sampling chooses a single token. Now here's something important. At this moment, the model has generated exactly one new token, just one. Not a sentence, not a paragraph, not even a complete thought, just one token. But a useful response requires many tokens, so the newly generated token is added back to the sequence, and the entire generation process runs again, and again, and again, one token at a time. This loop continues until the model generates a special end-of-sequence token or reaches its maximum response length. Only after all the tokens have been generated are they converted back into human-readable text. This final step is called decoding, and what ultimately appears on your screen as a sentence, a paragraph, or even an entire essay is simply the result of this process repeating hundreds or sometimes thousands of times at incredible speed. Now that we have the big picture, let's open up this pipeline and understand exactly what's happening at each step. The first thing to understand is that large language models do not read words. They read tokens. A token is simply a chunk of text. Sometimes it's a whole word. Sometimes it's part of a word. Sometimes it's punctuation. And sometimes it's even a space. Why split words like this? Efficiency. During training, the model sees huge amounts of text. Certain pieces of words appear repeatedly. Instead of memorizing every possible word, the tokenizer learns reusable pieces. For example, the ending ing appears in thousands of words, so it makes sense to treat it as its own token. This is OpenAI Tokenizer. Here the total words are 8, characters are 32, and the token count is 8. This tokenizer is built before the neural network itself. Think of it as a pre-processing step. The tokenizer creates a vocabulary. Every token in that vocabulary gets a unique number called a token ID. For example, "the" might become 342. France might become 18472. The actual numbers vary by model, but the idea is the same. These token IDs are what enter the model. And this explains something many people misunderstand. When an API says a model supports 4,000 tokens, it does not mean 4,000 words. Depending on the text, 4,000 tokens might be roughly 3,000 words or even fewer. So after tokenization, your beautiful sentence has been transformed into a sequence of integers. But there's a problem. The number 18,472 doesn't mean anything. It's just a number. The model still needs a way to represent meaning. That's where embeddings come in. At this point, we have a sequence of token IDs. But there's a problem. These numbers don't actually mean anything. If I tell you that the token ID for the word France is 18,472, what does that tell you? Nothing. It's just a label. And neural networks can't do much with labels alone. They need a way to represent meaning. So before these tokens can enter the model, each token ID is converted into something called an embedding. An embedding is simply a vector, a long list of numbers, something that might look like this. To us, it looks like a random collection of values, but to the model, these numbers carry information about the token and its relationship to other tokens. Now, you might be wondering, where do these vectors come from? This is actually the first place where the model's parameters come into the picture. Remember when we say a model has billions of parameters? Some of those parameters are stored in what's called an embedding table. You can think of it as a giant lookup table. Every token ID has a corresponding vector that was learned during training. So when the model sees token ID 18472, it looks up the learned vector associated with that token and uses it as the starting representation. These vectors weren't manually created by engineers. They were learned automatically from massive amounts of text during training. Over time, the model gradually adjusted its parameters until tokens that appear in similar contexts developed similar vector representations. You can think of these embeddings as coordinates inside a giant meaning space. Now, we obviously can't visualize thousands of dimensions, but if we simplify that space down to just a few dimensions, something interesting happens. Words with similar meanings tend to end up close to one another. For example, king, queen, prince, and princess might form one cluster. Dog and cat might appear close together in another. Programming-related words could form their own neighborhood, and medical terms might form another. This is one of the reasons language models can recognize relationships between concepts. Similar ideas often end up represented by similar vectors. Now, here's a question that confuses a lot of people. Does a word always have the same embedding? The answer is yes and no. Initially, yes. Every token starts with a fixed embedding from the embedding table. For example, the word bank starts with exactly the same vector whether we're talking about a financial bank or the bank of a river. But that's only the starting point. As the token moves through the transformer, it begins interacting with the words around it, and those interactions continuously modify its internal representation. So by the time the model finishes processing the sentence, the word bank in a finance article and the word bank in a geography article will have very different contextual representations. In other words, the starting embedding is fixed, but the final meaning is shaped by context. And this is where the majority of the model's billions of parameters come into play. The embedding table contains some parameters, but most of the parameters live inside the transformer itself. Those parameters are what allow the model to take a simple starting vector and gradually transform it into a rich, context-aware representation. So now, instead of meaningless token IDs, we have meaningful vector representations, and those vectors are finally ready to enter the heart of the model, the transformer. This is where most of the model's billions of parameters live. You may have heard numbers like 70 billion parameters or even 175 billion parameters, but what exactly are those parameters? Think of them as the learned weights of the neural network. During training, these weights are adjusted again and again across enormous amounts of text. Over time, they learn patterns about language, grammar, relationships between words, facts, and countless other statistical patterns found in the training data. When we use ChatGPT, those parameters aren't changing. The model is simply using those learned patterns to process our input. Now, inside the transformer, the most important innovation is something called attention. Imagine a theater performance. Several actors are on stage at the same time, but whenever someone speaks, a spotlight operator decides where the audience should focus. Attention works in a very similar way. As the model processes each token, it decides which other tokens are most relevant at that moment. Let's look at an example. The animal didn't cross the street because it was tired. When the model reaches the word it needs to determine what it refers to, the animal, not the street, even though the street appears closer in the sentence. Attention helps the model identify these kinds of relationships. And here's the important part. The model wasn't explicitly programmed with grammar rules that say what it refers to. Instead, these patterns were learned through the model's parameters during training. After seeing billions or even trillions of examples, the model gradually learned which relationships tend to matter in different situations. And this doesn't happen just once. Modern transformers use many attention heads simultaneously. You can think of them as multiple spotlights operating at the same time. Different attention heads can focus on different kinds of relationships. One head might focus on grammar, another might track references across a long sentence, another might focus on semantic relationships between concepts. All of these calculations happen in parallel, but attention is only part of the story. After attention gathers information from the surrounding tokens, that information flows into another component called a feed-forward network. If attention answers the question, what information should I pay attention to? Then the feed-forward network answers, what should I do with that information? Together, attention and feed-forward networks form a single transformer layer, and then the process repeats again and again and again, layer after layer. For example, GPT-3 contains 96 transformer layers stacked on top of one another. Many modern models contain dozens of similar layers. Each layer refines the token representations a little more. Each layer incorporates additional context, and each layer transforms the vectors into increasingly rich representations of the input. By the time the vectors emerge from the final layer, they no longer represent isolated words. They contain information about the entire prompt, the relationships between concepts, and the context needed to predict what should come next. And that's exactly what the model is about to do. Now comes the prediction step. Up to this point, the transformer has processed the entire prompt. It has analyzed the relationships between words, captured the context, and transformed the original token embeddings into rich contextual representations. Now, the model faces a simple question: what token should come next? Let's take an example. Suppose the prompt is, the capital of France is. At this moment, the model doesn't immediately output the word Paris. Instead, it evaluates every token in its vocabulary, and that's a huge list. Models like Llama 3 have vocabularies containing well over 100,000 tokens. So how does the model decide which tokens are more likely than others? This is where the learned parameters come into play once again. Using the contextual representation produced by the transformer, the model compares the current context against every token it knows. Tokens that fit the context will receive higher scores. Tokens that don't fit receive lower scores. For our example, tokens like Paris would receive a very high score. Tokens like Rome might receive a lower score, and completely unrelated tokens would receive even lower scores. These raw scores are called logits. At this stage, they're not probabilities yet. They're simply numerical scores that represent how strongly the model favors each possible next token. To convert those scores into something meaningful, we apply a mathematical function called softmax. Softmax takes all of the logits and converts them into probabilities that add up to 100%. Now, instead of raw scores, we have a probability distribution over every possible next token. For example, Paris might receive 64%, Lion might receive 12%, Rome might receive 7%, and thousands of other tokens would share the remaining probability. And this is one of the most important ideas to understand about large language models. The model is not deciding what to say. It is not searching for a hidden answer stored somewhere inside itself. What it's actually doing is predicting a probability distribution over possible next tokens. Every token gets a probability. Some are extremely likely, some are extremely unlikely, and your final response is simply one path through this enormous space of possibilities. The next question is, how does the model choose one token from that probability distribution? That's where sampling comes in. So now we have a probability distribution. Every possible next token has a probability attached to it. Some tokens are highly likely, others are possible, but less likely, and many are extremely unlikely. The question is, how does the model choose one token from all of these possibilities? This step is called sampling. The simplest approach is something known as greedy decoding. The idea is straightforward. Just pick the token with the highest probability every single time. If Paris has the highest probability, choose Paris. Then move on to the next token and do the same thing again, and again, and again. This approach is reliable, it's predictable, and for certain tasks, that's exactly what you want. But there's a downside. If the model always picks the most likely token, the responses can start to feel repetitive and sometimes a little boring. That's where temperature comes in. Temperature controls how adventurous the selection process becomes. Think of it as a creativity dial. A lower temperature makes the model more conservative. It becomes more confident in the highest probability tokens and less willing to explore alternatives. As a result, the output tends to be more predictable, more focused, and more consistent. This is often useful for tasks like coding, data extraction, or technical explanations where accuracy matters more than creativity. A higher temperature does the opposite. It flattens the probability distribution and gives less likely tokens a better chance of being selected. Now, the model is more willing to explore different possibilities. That can make the output more diverse, more surprising, and often more creative. But there's a trade-off. Push the temperature too high, and the model can start making strange choices. The response may become inconsistent, nonsensical, or drift away from the original topic. So temperature isn't changing what the model knows. It's changing how the model chooses from what it already knows. Think of it this way. The model has already generated a list of possibilities. Temperature simply influences which of those possibilities gets picked. Once a token is selected, the model can finally move on to generating the next token. At this point, the model has selected a token. Let's say that token is Paris. Are we done? Not even close. The model has only generated a single token. To continue the response, that newly generated token is added back to the existing sequence. So, the prompt effectively grows. Now, instead of predicting the next token after, the capital of France is, the model is predicting the next token after, the capital of France is Paris, and then the process repeats. The tokens are converted into embeddings. Those embeddings flow through the transformer. The transformer produces logits. The logits become probabilities. Sampling selects the next token. Then the cycle repeats again, and again, and again, one token at a time. This is how an entire sentence is generated, then a paragraph, and eventually an entire response. Now, if you've been paying attention, you might be wondering, wouldn't recomputing all of this for every new token be incredibly expensive? And you're absolutely right. Modern language models use an optimization called KV cache. Instead of recalculating everything from scratch, the model reuses information from previous steps whenever possible. This makes generation dramatically faster, but conceptually, it's still helpful to think of the model as extending the sequence one token at a time. Generate a token, append it to the sequence, predict the next one, and repeat over and over again until the model generates a special end-of-sequence token or reaches its response limit. Eventually, the model generates an end-of-sequence token or reaches a length limit. At that point, the token IDs are converted back into human-readable text. This step is called decoding. So the next time ChatGPT answers a question, remember what's happening underneath. Your words become tokens. Tokens become vectors. Vectors flow through layers of attention. The model predicts probabilities. Sampling chooses one token, and the process repeats one token at a time. There is no hidden script, no pre-written response, no sentence waiting inside the model, just probabilities, mathematics, and billions of learned patterns working together to generate text, one token at a time. And somehow, those numbers become language.